Hi everyone! Today we're going to talk about limiting reactants as well as excess reactants. This is the last part of chapter 11, which is the stoichiometry chapter. I'm also going to give you like 2 slides about something called theoretical yield, percent yield, and actual yield. And it's really, really simple. So I just threw in a couple slides on that. Let's start off with limiting reactants. So why do reactions stop? Reactions will continue to go or proceed until one of the reactants is completely used up. So a reaction is going to continue to go and react until one of those reactants is completely gone. That means that if one of them is used up, then one will be left in excess. The limiting reactant will limit the extent of this reaction. So if the limiting reactant limits the reaction, then it's the limiting reactant that will determine how much product can be formed. So you kind of saw on your POGL on Friday that the limiting reactant will determine how much product you can make. So I know on one part of the POGL they had you do something like with cars. And if you were limited by how many cylinders you had, then that would limit the amount of cars that you could make. So that's what they mean here by limiting reactant will limit the extent of the reaction, and that limiting reactant will determine how much product can be made. The excess reactant is just something that's left over. It's in excess, and it's just something that will remain unused. Okay, so determining the limiting reactant is really important because we need to know how much product is going to form, and the amount of product that forms is dependent on the limiting reactant. So it's really important that you understand the amount of the product that is formed in a reaction is solely dependent on the limiting reactant, okay? So in this reaction, I have 3 nitrogen molecules and then I have 3 hydrogen molecules. After the reaction, I'm going to get 2 ammonia molecules, and then I'm going to have some leftover nitrogen. So based on this reaction, and again, this would be an example of a particle model. Why is this a particle model? Because I see that I've drawn particles for you, so it's a visual representation of what's happening on a microscopic level. That just means that it's on a smaller scale. So I have 3 nitrogen molecules, 3 hydrogen molecules. Well, if I come over here to my products, I see that I've used all of my hydrogen, but I haven't used all of my nitrogen. So if I'm looking at this on a particle level, what here would have been my limiting reactant? My limiting reactant would have been my hydrogen. It's all used up. It's all bonded here. And what's excess is my nitrogen. I'm left over with these 2 nitrogen molecules. I didn't need all of that nitrogen in this reaction. Okay, so that's a visual way that we can determine limiting and excess reactants. But it's not always going to be that easy because we can't see things. We can't see atoms or molecules at this level with our eyes. So we're going to have to do some calculations instead. So let's say that we want to practice calculating the product when a reactant is limiting. So I gave you this equation here. We have sulfur plus chlorine is going to make disulfur dichlorine. Okay? And that's a nice balanced equation as well. Okay, let's say if 200 grams of sulfur reacts with 100 grams of chlorine, I want to know what will the mass of disulfur dichloride be if I'm producing that. So remember that the mass of disulfur dichloride is going to be dependent on which one is my limiting reactant. So it could be this one or it could be this one. I don't know. I'm going to have to figure out first what my limiting reactant is. Because if I need to find the mass of disulfur dichloride, it will be dependent on one of these things. So I have to figure that out first. So let's break this down into steps. Really easy steps. So we're going to first determine the amount of moles of reactants. So you were given 200 grams of sulfur and then you are also given 100 grams of chlorine. I just want to take those masses and I want to convert those to moles, and that's exactly what we did here. I had 100 grams of chlorine. I found the moles of chlorine. My moles is 1.41 moles of chlorine. I did the exact same thing for sulfur. I started off with 200 grams of sulfur. I just want to convert that to moles. So since I have 8 sulfurs there, that's why it's going to be that 256. And remember, since I had 2 chlorines, that's why it's 70, not just 35. So now I've taken my mass of both reactants and I've converted those into moles. I have 1.410 moles of chlorine, 0.7797 moles of sulfur. Okay? So now I've done my moles. Your second step, we want to convert the moles of the reactants to the moles of the product that we're trying to form. And we want to do that by using a mole ratio. So based on step number 1, I just calculated these two things. I found that I had 1.41 moles of chlorine, and I found that I had 0.7797 moles of sulfur. So I want to convert that, both of these reactants, to moles of disulfur dichloride. And I can do that by using a mole ratio. So all of these steps are very similar to those stoichiometry steps that we just got done doing. I had my moles. I'm going to have to use my reaction, remember, for a mole ratio. So according to my reaction, if I wanted to do moles of chlorine to moles of sulfur disulfur dichloride, there's 4 moles of disulfur dichloride to 4 moles of chlorine. So my number here just stays the same. If I look at my moles of sulfur, I used a mole ratio to get from moles of sulfur to moles of disulfur dichloride, and I see that I have 3.1188 moles of disulfur dichloride that could be produced based on sulfur. So based on these answers, I am comparing the exact same thing now. I'm comparing moles of sulfur disulfur dichloride, to moles of disulfur dichloride. All the difference is, one of these amounts of moles came from chlorine, the other amount of moles came from sulfur. So whichever amount of moles is smaller, that is my limiting reactant, because it means that I can't produce as much of that product. So which one here would be my limiting reactant? Would it be chlorine or would it be sulfur? In this case, it would be chlorine, because chlorine can only produce 1.410 moles of disulfur dichloride, but sulfur can produce 3.1188 moles. So sulfur can produce a lot more than chlorine can. So I must be limited in my reaction by what chlorine can make. So chlorine is my limiting reactant, okay? So now that I know that chlorine is my limiting reactant, I can find the mass of disulfur dichloride that will be produced. So that's my third step. So remember, the first step was I had grams, I needed to convert those to moles, and that was for both reactants. The next step was that I'm going to take those moles, use a mole ratio to convert it to the moles of that product, which is what we did right here. Then based on whichever one is smaller, that will be my limiting reactant. So that's how I can identify which one my limiting reactant is. My third step, which is to find the mass of the product formed. Remember, we started off here with 1.41 moles of chlorine. I used a mole ratio to get to moles of disulfur dichlorine. And then I can go back to molar mass to find grams of disulfur dichloride produced. So all of these things are just stoichiometry steps again. Okay, so we ended up finding, that 190.4 grams of disulfur dichloride could be produced based on my limiting reactant chlorine. But now, I want to know how much excess reactant is going to be left. And I know that if chlorine is my limiting reactant, then what in this situation was my excess reactant? Well, we know that had to be sulfur. So how much sulfur actually reacted in the reaction, and then how much do I have left? So based on this, there's steps to these as well. First step, we want to make a mole to mass calculation to determine the mass of sulfur needed if my limiting reactant is chlorine. So I have my limiting reactant chlorine, and the amount of moles that's going to react in my reaction will be based on my limiting reactant chlorine. So I know I had 1.41 moles of chlorine. I want to convert that to moles of sulfur. So we did that here. We get 0.3525 moles of sulfur. So that means this is the amount of moles of sulfur that is actually going to react in the reaction. So if I want to know how much mass of sulfur reacted in the reaction, now that I have my moles of sulfur, I can use molar mass to find how many grams, which is exactly what we're doing. I just calculated 0.3525 moles of sulfur. I used molar mass, and I found that 90.42 grams of sulfur is needed to make this reaction go, to completely use up that limiting reactant of chlorine. But now I want to know, last question, how many grams of sulfur are left in excess after this reaction happens? And I know that I started off with 200 grams of sulfur. I know that 200 grams of sulfur was available. And I only used 90.42 grams. So if I want to know how much is left, I'm simply just going to subtract 200 grams minus whatever I needed in the reaction, 90.42. So that means that the amount of sulfur that I have left is 109.6 grams. Okay, so using an excess reactant can sometimes speed up the reaction. It can make the reaction go a little bit faster. And using an excess reactant can also drive a reaction to completion. And it just means it's kind of like acting in a catalyst as a way. So it's just because we have some excess reactant present makes that reaction just go a little bit faster. Okay, so the mass of the final product in a chemical reaction is going to be based on what? Would it be A, the amount of excess reactant? Is it B, the amount of limiting reactant? C, the presence of a catalyst? Or D, the amount of oxygen present? So the mass of that final product in a chemical reaction is always going to be based on what? We should be saying B. It's the amount of the limiting reactant. That limiting reactant, the product's mass will be completely dependent on the amount of the limiting reactant that I have. Okay, so this is a really great practice question for you, and it is, what is the excess reactant in the following reaction if you're starting off with 50 grams of each reactant? So that's saying I'm starting off with 50 grams of phosphorus, 50 grams of oxygen, and then I'm going to make tetraphosphorus decoxide. So I will let you try this one on your own, and I've highlighted the answer here for you in your notes. So you should get phosphorus as being your the excess reactant. Okay, very lastly, we're going to do another example of how we would calculate a limiting reactant as well as an excess reactant. But I just want to go through these few slides just really quickly. So the theoretical yield is something that will tell us the maximum amount of product that can be produced from a given amount of a reactant. So theoretical yield just means this is the most product that can be produced based on what I'm given. The actual yield is the amount of product that we're actually producing in an experiment. So there's a difference between actual and theoretical. And theoretical, of course, is what we would want to strive for every time in a lab. But stuff happens. Sometimes we get some product like on the sides of our beakers. Sometimes we can't get all of the product out of a little well plate, and all of those things factor into how much product I'm going to get. So if I were an awesome chemist and nothing ever went wrong, I would always get the maximum amount of product every time. That's my theoretical yield. But we're human, and there's always error in a lab. We can't do something with 100% efficiency in the lab. So I will always end up getting something called an actual yield. And that's just what I'm actually getting after this chemical reaction has gone through. Based on the actual yield and the theoretical yield, we can calculate something called the percent yield. And the percent yield is just a ratio of the actual yield over the theoretical yield, and since it's a percent, we're going to have to times it by 100. So percent yield is just what I actually got in the lab versus what I could have made, what I could have produced in the lab, and then times 100. So let's say, for example, if the theoretical yield of a chemical reaction